Hello, welcome to this lesson, which is an introduction to forces. It's the first lesson in a series, and in fact the lesson itself is split into 4 parts, of which this is part 1. And in part 1 we're going to take a look at some introductory background information and then talk about weight and the formula W equals mg. Weight is something that we deal with frequently when doing force problems, so we need to talk about it briefly. In the other 3 parts of this first lesson, we'll talk about normal reaction, friction, and tension and compression, which again are forces which frequently come up in problems. During the lesson there'll be a few questions, and at the end some calculations. If you want a pen, paper and calculator, now is a good time to pause and get them. Let's briefly say what you should already know. Probably the most important thing you should be familiar with is how to apply vectors. Do you understand the basic concepts? Magnitude of a vector, addition, subtraction, use of components. These are covered in separate video lessons if you need to look them up. When we study forces, we generally divide the subject area into 2 broad areas, statics and dynamics. You probably guess from the name, statics means studying forces in systems that have no motion, not moving, whereas dynamics means studying forces in systems which have some sort of motion, moving. Quick example of each. A statics problem, simple statics problem, would be the one shown in the diagram. 3 kilogram mass suspended by 2 ropes. Find the tension in each rope, given some information. We're not going to do that now. That's the sort of thing we'll be learning how to do later on when we cover statics. Dynamics, another simple example of a problem. Here's a block on a slope. You're given some information. The question is, how long does it take it to slide down the slope? A simple dynamics problem. Okay, before we move on to weight, here's a few quick true or false questions for you to try and see if you understand some basic information about weight. This is not stuff I've just covered, it's stuff I expect you to be already familiar with. So, let me read through the questions quickly. Question A, true or false? A force means a push or pull acting on an object. B, a force always makes an object move. C, a force can be a scalar or vector. D, a force has SI units of kilograms. And E, a force can be negative. If you want to pause the video, you can think about those. I'll go through the answers in a moment. Okay, let's go through those. The first one, a force means push or pull acting on an object. True, that's a simple way of describing what a force is. Nothing more than that. A force always makes an object move. False, you could go outside and push against a large building and you won't make the building move. So a force doesn't always make an object move, though of course in some circumstances it can do. And a force can be a scalar or vector. False. A force is always a vector. It has a magnitude and it's got a direction, and you can add vectors using vector addition. It's not a scalar, it's got a direction. Force has SI units of kilograms. No, it doesn't. That's false. The unit of any sort of force is called a newton. By the way, make a note that newton, if you write it in full, has got a small n. We only use a capital N when writing it in full if talking about the name Sir Isaac Newton. However, the symbol for the unit newton is a capital N. And the last one, a force can be negative. Absolutely true. We often use negative values to indicate a direction. For example, a force to the right might be indicated as plus 5 newtons, a force to the left might be minus 5 newtons. Okay, let's move on and talk about weight, which is a very important force that comes up in many problems. Let me give you a quick definition of weight. Weight is the force acting on an object, so that's a type of force, due to the gravitational pull of the Earth. And you might say, well, we could have a weight if we were on the moon, so let's extend that slightly and say, or other celestial object, a planet or moon. If you're at the surface or near the surface, you have what is generally called a weight due to the object attracting you by gravity. Quick diagram to show you what's going on. Blue disk is the Earth, a couple of objects. In fact, the objects are being attracted towards the centre. It's a spherically symmetric object, the Earth, and we're being pulled towards the centre of the Earth. That's what we mean by downwards. Our sense of downwards is actually towards the centre of the Earth. For most simple problems in statics and dynamics, we can think of the weight acting vertically downwards. We don't have to worry about the fact that the Earth is curved. And there's a simple diagram, box resting on the ground, red arrow shows the weight. I've drawn the red arrow starting at the centre of the box, its centre of gravity, pointing vertically downwards. And here's another question for you. True or false? While an object is falling, it is weightless. If you want to think about that, pause the video now. And let me tell you that is false. It doesn't matter whether the object's going up or coming down if you throw it. It doesn't matter if it's tilted over while it's in the air. The weight is always pulling the object towards the centre of the Earth, downwards. And just because it's been thrown in the air doesn't mean that the force of gravity suddenly magically gets switched off. The pull of gravity is always there. Some people have this impression that while you're falling, you are weightless. But let me just clarify that briefly by telling you what we mean by apparent weightlessness. Suppose you're in a lift, which is a yellow box, and the cable breaks so the lift starts freely falling. In fact, you fall and the lift falls, and you're both being accelerated downwards because you have weight. Gravity is pulling you downwards. And you and the lift are freely falling. You feel weightless, and it seems to you like you're weightless because inside the lift you appear to be able to float around in your environment in the lift. But of course you're not really floating. You're falling downwards at the same rate as the lift is falling downwards. You're being accelerated downwards by your weight, and that's the same rate as the lift is falling downwards. So it appears to you that you're weightless, but you and the lift still have weight, which is causing you to accelerate and being pulled downwards. Hope that's clear. Let's talk a bit more about weight. This diagram, usually weight shown with an arrow pointing downwards, labelled W. We already know that weight is the force of gravity on an object, and it's measured in newtons. Weight is not the same as mass, so people get confused. People say the weight is 5 kilograms. That's okay in normal day-to-day parlance in a shop, but when you're talking physics, you cannot say things like the weight is 5 kilograms. Weight is not the same as mass, and mass is measured in kilograms. You'll learn a bit later on what we mean by mass when you learn about Newton's laws of motion, but for the time being, the mass is some quantity which doesn't change, isn't affected by the pull of gravity. So do not confuse mass and weight in physics. Here's a quick question for you. Let's suppose your mass is 70 kilograms. Are the following statements true or false? Your mass is less on the moon than on Earth, and your weight is less on the moon than on Earth. Are they true or false? If you want to think about them, you can pause. And the first statement is false. If you're 70 kilograms and go to the moon or anywhere else in the universe, your mass remains 70 kilograms. That doesn't change. However, your weight is less on the moon because the pull of gravity on the moon is less than on Earth. So the second statement is true. It's a low gravity environment on the moon. In fact, you weigh about 1/6 of your normal Earth weight if you went to the moon. Let's do the key part. How do you find the weight of something if you know its mass? Well, the two things which control the magnitude of weight, the size of weight, the two factors are the mass of the object. So if you've got two objects and one has got twice the mass of the other, it will weigh twice as much. It's proportional to mass. But the other thing that affects weight is the gravitational field strength of wherever you happen to be. And this quantity, gravitational field strength, is usually given the symbol small g, and you probably met it before. Don't use a capital G, uppercase G, because a capital G means something different in physics. And G is sometimes called the acceleration due to gravity or acceleration of free fall. These are all different names for the same thing. And I hope you've probably met G before. G can be measured in units of meters per second squared, like an acceleration, or newtons per kilogram. And it may not look it, but these two units are actually equivalent to each other. Near the surface of the Earth, we normally take G, if we want an approximate calculation, as about 10 meters per second squared, or 10 newtons per kilogram, same thing. That's okay for approximate calculations. If we need to be a bit more accurate, which is usually the case, we'll take G as 9.8 or 9.81 meters per second squared, newtons per kilogram. You may note that actually G, if you measure it accurately, varies from place to place. But for most problems, using this kind of average value of 9.81 meters per second squared is okay for problems at or near the surface of the Earth. If you're on the moon, it's different. If you move a long way from the Earth, the pull of gravity gets weaker, you need a smaller value. But for most problems, 9.81 is a good value to use. I hope you've met before the fact that we can have a negative value for G. If you've done the lessons on projectile motions, a negative value can be used, minus 9.81, if the problem requires a sign convention, such as upwards positive, downwards negative. We may have G minus 9.81 meters per second squared, indicating it acts downwards. However, the really important bit is this. If you want to work out weight in newtons, because it's a force, how do we do it? We multiply the mass in kilograms by the gravitational field strength in, well, meters per second squared or newtons per kilogram. I've put newtons per kilogram here because you can see that the units balance very neatly. And the reason that formula is true is because of how we define gravitational field strength. We define it such that this formula is true, but that's not the current topic. The formula is normally written in symbols, W equals mg. Remember to get the units right. The mass has got to be in kilograms, and as marked, as shown, those units. That's a very important formula we use over again. Let's just summarize it with its own screen. There it is, W is mg. Can you remember that? You shouldn't have to look it up. It should be instinctive. Now, it's time for you to do 3 simple calculations before we finish this part of the lesson. So here they are. When you do these calculations, can you use G as 9.81 meters per second squared or newtons per kilogram? And here are the questions. I'll quickly read them, then you can pause and do them for yourself. 1. What's the weight of a 1.2 metric ton truck? Now, I hope you know that a metric ton is the same as 1,000 kilograms. So 1.2 metric tons, or just tons, is the same as 1,200 kilograms. Question 2, a crate has a weight of 250 newtons. What's its mass? And the final one, what's the weight of 210 milligrams of salt? Now, it can be a bit confusing because mg looks a bit like mass and gravitational field strength, but I hope you can see from the context of the information that 210 mg here means 210 milligrams, and I've written milligrams just to remind you. So you've got to be a bit careful when you read through questions to make sure you fully understand the information. Pause the video, try all 3 of those questions. Let's go over them. First one, very easy. W is mg, put the numbers in, 1200 kilograms times 9.81 newtons per kilogram. Round the answer to three significant figures, that's sensible, 11,800 newtons. Next one, work backwards. W is mg, so if you rearrange that, you should be able to get m is W divided by g. That's 250 newtons over 9.81 newtons per kilogram, and to three significant figures, 25.5 kilograms. And the final one, well, two stages. The first stage is to work out the mass in kilograms. We're told that the mass is 210 milligrams, or we are meant to realise that the mass is 210 milligrams. How do we get that into kilograms? Stage 1, turn it to grams. 210 milligrams means 210 times 10 to the minus 3. Because milli means 1,000th, 10 to the minus 3. That's in grams. How do we get from grams to kilograms? Well, we divide grams by 1,000 to get kilograms. Same as multiplying it by 10 to the minus 3. So now we've got 210 times 10 to the minus 3 times 10 to the minus 3 again, gives us 210 times 10 to the minus 6 kilograms. Now we can work out the weight, mg, 210 times 10 to the minus 6 times 9.81. And it comes to 2.06 times 10 to the minus 3 newtons. If you wanted it a bit more neatly, you could say it's 2.06 millinewtons. Okay, we are done. Thank you for watching part 1. In part 2, if you want to watch them, we'll cover normal reaction, which is the next part. Then later on, friction and tension and compression. Thank you and goodbye.